Well, g'day flatties and globe defenders, it's Critical Think from Down Under. A little while ago I took this observation of a ship that's under high refractive conditions, unusual refraction on the day, where this is taken from an elevation of very close to the water, and you can still see all of the ship, but it's compressed in the bottom there, so when you compare it with the observation taken higher up, you can see, if I just go here slowly, that the ship is compressed upwards, the water appears to rise up, and my question to flat earthers was, really, why does the water appear to rise up? So there's been two responses that I know of, one by Gary Wybenga and one by Exploring the Plane. They both go by similar principles in that a change in the viewing height somehow causes the bottom of the ship to be compressed. I say somehow because there's no real evidence of how this could happen. So today we're going to look at Exploring the Plane's video on this question. Starts out by saying objects at eye level compress and eventually sink into the horizon. Now, to be perfectly honest, I really don't know what he's on about here. What I think he's talking about the effect of perspective, where objects shrink into the distance. Sinking is not quite the right word in my book. Objects do shrink into the distance because of perspective, but they don't sink into the horizon. So I really don't know what he's talking about there. And he says here, that's just how we see because of the inevitable convergence and limitations of our vision. What else would we expect? Well, I'll tell you what I expect. I expect that as objects move away into the distance, they shrink in size in all directions, and as they get too small, you're not able to see them anymore. So this is known and well-known facts. Nobody's arguing about how perspective works, so I don't see how this has anything to do with my ship, which is not moving away into the distance. So, I don't get it. I don't get it why this is a factor. But let's carry on. Yes, so this is my video. I'm demonstrate how a ship is subject to this compression, but he's added when at eye level. Now, that's nothing to do with me. That's his addition. Has nothing to do with eye level, and I'll demonstrate that. So, okay, Exploring the Plane says it's demonstrated this before. Well, I've still not seen anything that's put up by Exploring the Plane that shows how this exact test has been done, but it doesn't matter so much. But if you're going to say something like, we have demonstrated this before, then you should follow that with the evidence. Otherwise, it's just an empty claim. Again, nope, it's not an argument. Now, I looked at the proportions of this ship and I thought, wow, that's compressed vertically. And I was right about that. But I'm not really sure what the nope refers to. Is the nope the fact that it's not compressed, or is the nope because of he doesn't think that there's refraction? So nope doesn't really tell us anything, and there's no evidence. So as a matter of fact, with this ship, in the original video, this here was actually stretched in the original video. Now, I didn't mean it to come out like that, but when I looked at that, I did think it was stretched, and yes, it was. So nope doesn't really tell us much, and in fact, yes, it was compressed vertically. So my blink test shows, of course, that the bottom of the ship is compressed up. And so the comment here is, as we've often said, this is caused by convergence at eye level. This is supposed to be an example, and it doesn't even look anything like my ship. My ship, you can still see all the bottom, and I'll just go back to that, and I'll go back to the compressed part. You can still see all the bottom. In this example, this is a clear case of the bottom missing from someone because of obstruction by the curvature of the Earth. But he wants to claim that this is because mountains distort, compress and morph into the horizon. So there's no known mechanism by which this can occur. This is something that's just made up to fit the narrative, because the Earth must be flat. That can't be bottom missing because of curvature. But if you analyse this correctly, first of all, these two images, the one above and below, are taken from different angles, which different parallax, so it makes it a little bit difficult to compare them exactly. Plus, there's no evidence there of compression. It's only this exploring the plane says it's compression because he can't see the rest of what was below this horizon here, and so he's called it compression. But there is no evidence of compression. And if you look closely there, you can see that there is an inferior mirage. This roller coaster is not compressed. If it was compressed, it would look a lot different to that. So I've got my own blink test for that. And the tops of the mountains, because it's different, taken from a different angle, it's not a very good comparison, but you can see the tops of the mountains remain fairly consistent. But there's somehow a magic process that only works when you're close to the ground that compresses all the rest of that image into a fine line. And there's another thing about this, is that when you're at a higher elevation, there is no such compression at that eye level. It's only when the eye level and the ground are close together that this magical compression takes place. Here the narrative on this picture is that as we get lower and our visual angle declines, the integrity of the whole image starts to break down bottom first, and this is nothing to do with refraction. Well, anybody who's made any observations over water will know that this is complete bollocks. This has everything to do with refraction. Now, on certain days over water, the atmosphere gets more turbulent and difficult to see through as you get closer to the water. And the effects are varied. Sometimes it can be compression, sometimes inferior mirage. But from higher up, you're out of that highly refractive layer where there's sharp temperature differences and water vapor differences. And when you're higher, from 50 feet high, you get a much clearer picture. Now, that's all it is. It has nothing to do with the visual angle. And I will demonstrate that, because I have some pictures that are a very low visual angle that were taken on days when there was very good visibility, and you don't see this. The other thing about these pictures taken minutes apart is that there's this somehow supposition that there's a horizontal distortion because this 58 pixels and this 43 pixels, there's no horizontal changes like that. They're not normally observable, and in this case it's not observable either. So if I just take this here and copy this and paste this and move it. Now 58 pixels seems a little bit less, and it wouldn't, that must have come off a 720 pixel picture, but it doesn't matter so much. But you'll notice that this here has a building there, which is this building here, and so it's not really compressed horizontally. It's just that this one here you can hardly see anything, and he's mistaken that and where that building comes to over here, and there's that smudge there, which would relate to that building over there. So there's no horizontal compression. Now, the thing to note here is that the sea level appears to rise in relation to the cranes that are higher out of the... So, again, this is just incorrect. No explanation of what is incorrect or why is it incorrect. It is true that the sea level appears to rise in relation to the crane. So just the statement of incorrect is incorrect. So there's no argument, no reasoning, and just derp. You might as well just have said derp. I said we know that the earth is curved, and he just says no, we don't. No evidence. No evidence, when in fact it is a well-known scientific fact that the earth is curved. We know that the earth is curved because of thousands of years of study and measurements and navigation and I'm not going to list them all here, but yes, we do know that the earth is curved, and we do know that this surface is curved. Now, you just can't say no, we don't. You have to have some kind of evidence, some kind of measurement, other than no, we don't. So this is how he explains the fact that the ship is compressed from the bottom up, on the bottom, and not compressed at the top. The sea level appears to rise. So let's go here. There is no refraction. The sea has not risen, and the ship is not loomed up over the horizon. There is no curve. As a matter of fact, it is possible that this observation, you could get a similar observation like this on a flat earth if there was compression happening. And that's been demonstrated by the fish-taking experiments, and we'll get to show some of that. Convergence is occurring because the bottom of the ship is level with the observer, and this is important. I'm not really sure why that's important. Why does the observer have to be near the bottom of the ship? Why doesn't convergence occur when the observer is level with a different part of the ship? What's so special about the bottom of the ship? And he says, the visual angle has become unresolvable. Well, no, the change in your viewing angle to that ship does not change when you go up and down. It's only the angle relative to the surface that changes. And this is the thing that all the flat earthers seem to get confused. Just a minute, I'll bring up a picture. So when you change height from, say, 15 metres down to 1 metre, the only angle that changes is the angle between the surface and the observer, not the angle that the ship is viewed at. The ship itself is vertical. So if we were to assume that the ship is vertical, then this angle is 89.9 something degrees, and as you move down it hardly changes at all. That very, very small change does not explain any huge difference that we observe in the compression. So first of all, this angle between the horizontal and the observer changes by very, very little. This angle to the ship itself is very close to 90 degrees, so there's no appreciable change in angle at all. It's just something that they make up to try and explain away the unexplainable. So here's a picture which shows roughly where the eye level is on a ship. So if I'm at my higher point of 15 metres, that's where my eye level is on that ship. And why is that part not compressed? Why does the eye level have to be at the bottom of the ship? It doesn't make any sense. And this diagram here, over here, has nothing to do with this situation. So this is more or less perspective lines there, but perspective lines only apply to horizontal surfaces. So you see, as the horizontal surface moves further away, the objects become closer together on that surface. That's true, but not on a vertical surface. That doesn't apply. This diagram doesn't apply to a ship or a wall or a building which is at a constant distance from the observer. It's not getting further away. It's at the same distance. And they say mountains in the distance compress and lower into the horizon in a similar way, which is why angular size is not maintained over distance. Okay, not really sure what the point is. We know what perspective is. We know how it works. This image, changing my observer height, has nothing to do with perspective. The object remains pretty much the exact same distance away. So this here is a bit of a red herring. The convergence, because of perspective, is not applicable in this case. It's very confusing. So really, no, I'm going to discount that altogether. Well, I've gone on long enough for this, and I'm going to take a pause here, and I'll continue on in a second part. I think we're about halfway through. There's so much wrong here to be addressed. I didn't feel right about doing it quickly, so I thought I'd make my way carefully through it. So there'll be a part 2 to finish this off. Thanks for watching, and watch out for part 2.